These are the solutions to Chapter 8.1 textbook written homework. We start with problem number 14. Looking at problem number 14, we start with a picture of what appears to be a normal distribution. The normal distribution, again, has this shape, has inflection points here, has a high point, starts low, goes high, and then comes back down. It's symmetric, it's bell-shaped, all the language we've used before. The only thing on this case, this is what from we learned in class, what's called a sampling distribution, meaning that a sample was taken, multiple samples were taken from the population, and then we drew a distribution of the sample means of all of those samples. So again, imagine we were to have a population and we take a sample, get that mean, take a sample, get the mean. So we do this multiple times. So it's a sampling distribution of the sample mean. And so when you do take those samples from the population, you end up with a normal distribution. And so that's what we're looking at here. That's what we have on problem 14. Since this is a normal distribution, what's the value of the mu? The mu of x hat, what is that? That's right here in the middle. That is equal to 12. That's A. Part B, what is the value of the standard deviation of the sampling distribution? Remember, that's also called the standard error. It's another word for it because this is the standard deviation of the sampling distribution. It's called the standard error. What's that value? We can see in this case 0.05. That's how we've been marking those off. Part C, if the sample size is 9, that's a very small sample size. And so remember, we like larger sample sizes. That would give us a better distribution, or more, it would assure us that we have enough in our sample to kind of make these conclusions, to draw these conclusions. So it's a small sample size. So what's likely true about the population? Since we use small samples and it produced a normal population, we assume that since it's less than 30, we assume that the population must be normal. So if we did a sample, the population must be normal because we got a normal distribution here with a very small sample size. So the population must be normal. Okay, and so part D, if the sample size is 9, what is the standard deviation of the population? What is the standard deviation of the population? Now we have the standard error is 0.05. So in order to determine the standard deviation, what you need to remember is the standard error, or the standard deviation of the sample, the distribution. That's the formula we have, square root of n. So in this case, we have 0.05 is equal to the standard deviation divided by the square root of 9. And so in that case, you end up with what that leads us is to the standard deviation is going to be equal to 3 times 0.05. The square root of 9 is 3. The standard deviation of the population is going to be equal to 0.15. We now move on to problem number 18 from the homework. Simple random sample size 20 is obtained from a population with a mean of 64 and a standard deviation of 17. And of course, now that again, here's the population. So we're kind of trained into now just going ahead and drawing a normal curve. Again, this is the population. And so we know the mean is 64. Standard deviation 17. This is the population. Okay. And then we can mark off, of course, the standard deviations and so forth. We'll save that. So part A, what must be true regarding the population? What must be true regarding the distribution of the population in order to use the normal model? In order for us to use all these statistical tools that we're doing, what must be true about the distribution of the population? Assuming that this condition is true, describe the sampling distribution x bar. So meaning that if we took a whole bunch of samples from this population, a whole bunch of samples of size equals 20, what must be true? The population must be normal. Must be normal. Must be normally. Let's do normally distributed. Distributed. Must be normally distributed. If this is the case, then we also know that I drew it here, but it must be normally distributed. So that we can apply these rules here. And remember, it's also must be normally distributed because from there, our sample size is 20 and needs to be bigger than 30. We like them bigger than 30. So as if it's 20, then it's going to give us this. And so since now we have to assume it's normally distributed to apply these rules, what we know is that the mean of the sampling distribution, if we pull samples of size 20, would be equal to 64, and then that the standard deviation of the distribution, if we pull sample sizes of n equals 20, is going to be equal to 17 divided by the square root of 20, and you get approximately 3.801. Now we're going to use that information to answer B, assuming the requirements described in part A are satisfied, meaning that it's normally distributed. Then we can apply the normal rules to this. Then we can use the normal calculator. What's the probability that the mean is greater than 67.3? And so in this case, we would go to StatCrunch, 67.03. We're going to need some key information here. Stat calculator, normal, and we have to change these values. The mean is 64. The standard deviation is 3.801, or the standard area. So we're using what's called the adjusted standard deviation right here. The standard error, the adjusted standard deviation, and we want to see if it's less than 67.3. And so then you put here 67.3, less than, and we only have those two options, so less than there. 0.807 is our answer there. And so the answer to that is 0.8078. And again, what does that mean? That means if we take 100 simple samples of size equals 20, from that population, we would expect around 80 or 81 of those samples to have a mean less than 67.3. That's what that number means. There's an 80% chance that, or 81% chance that if we took a random sample of n equals 20, that the mean would be less than 67.3. And so that's the answer for B. For C, assume the requirements are described. So it's the same question. Probability that this is greater than 65.2. And so we're going to do the same thing here. Go back to here. 65.2 is our number. 65.2, compute. And so then you get 0.2. I want it to the right, sorry. So now we get 0.736 is our answer for that. 0.736 equals 3761 or so. Okay, so that's the probability there. And again, I know on StatCrunch they ask you this question, so I'm going to write one sentence out, the interpretation of that, just to kind of really solidify the idea for you. So, so what does this mean? That if we take 100 simple random samples, let's see if I can fit it in. Simple random samples of n equals 20. Then about 37, this is where it's coming, about 37 of the samples will result in a mean greater than or equal to 65.2. So I just wanted to write that out. You could also look in the book. I think they write out the full description if you look at the solutions in the book. And to finish this up, compared, what do we got going on in, here? Compare the results obtained in B and C with the results obtained in, compare the results obtained in parts B and C with the results obtained in parts B and C of problem 17. We didn't do 17, so it's kind of hard to kind of fully complete that. What effect does increasing, the most important question here is what effect does increasing sample size have on the probabilities? Why do you think this is the case? So in part D, we talked about that a little bit. It's in the lecture there a little bit, but in part D, what happens is the effect depends on and so the effect depends on really depends on the nature of the probability. And we didn't do, again, problem 17. They did the exact same problem with a smaller sample size, and the probabilities altered. One increased and one decreased. So again, don't worry too much about this one. This is since we didn't really compare, it's a really kind of deep idea. That's problem number 18. Problem number 26. Looking at problem number 26 here. Time spent in drive-throughs, quality control. And so looking at the situations, determine that the mean time spent at the window was 59.3 seconds. And then we also have the standard deviation of 13.3. The distribution of the time at the window is skewed right. And so we don't have a normal situation. So what allows us then to apply some of these normal rules? And so for question A, to obtain probabilities regarding a sample mean using the normal model, meaning using the rules that we've been using, the normal calculator, what sample size is required. So the only reason that we could apply these rules if we're going to do a sampling distribution and needs to be greater than or equal to 30. The sample size, right? Sample size must be at least 30. At least 30, and then we can apply the normal model with that because we learn from the central limit theorem, and that's what it says. We can apply these rules as the sample sizes get bigger, the normal the distribution of the sample means become normal, and so that's the central limit theorem. Part B, since now that the manager wishes to use a new delivery system, a random sample of 40, so we have a large sample size right there, results in a sample mean time of 58.6 seconds. What is the probability of obtaining that? What's the probability that it's, what is the probability of obtaining samples 56.8 or less, sorry, 56.8 seconds. So that's what we're calculating there. Assuming that 59.3 is what the population is. So if the population is 59.3, what is the probability that we would get 56.8 when 40 cars came? And so in this case, we would have to then, we know what the mean is. It's going to be 59.3. We need the standard error, or the standard deviation of the distribution of means, and that's going to be 13.1 divided by the square root of 40. So we need that calculation right there. And when we do that calculation, we get 2.071. And so then we're going to put that into StatCrunch. The mean was 59.3. Let me make sure I get these numbers right. 59.3 and 2.071. Oh no, open up the wrong stuff. 2.071, and we're checking to see what's a probability that we would get a time 56.8, less than 50.68, a mean time of less than 56.8, less than or equal to, and so you get 0.1137. So that's the answer for this one here, 0.1137, or about 11% chance that you would get this value. Part C here. Looking at that, treat the next 50 cars that arrive as a simple random sample. There's a 50% chance the mean time will be at what or below. So in this case, our mean is still going to be 59.3. We need another, we got to find the adjusted standard deviation or standard error. And so it's 13.1 divided by the square root of 50. And so on that answer, what we get there with that value there, we need to go ahead and do that calculation. 13.1 divided by square root of 50. Square root of 50, and then that equals 1.852. 1.852. And so what's really happening is now we're given the percentage. And so what we're really looking at on this problem when we go through it, right, is where arrives the next to the cars, there's a 15% chance the mean time will be below this. And so what we're really looking at is a value like this, 0.15. So we're looking for that value right there. So in this case, we would go to the normal calculator. Get that value, I need to change that to 1.85, 1.852 or 1.85. I'm clearing this out, and I'm going to put 0.15 here, and so that's how you're going to use it, because we're given the percent, and so now we know 57.38 is going to be our answer there, 57.38. So there's a 15% chance. There's a 15% chance that it is 57.38 right here seconds. So the answer is 57.38 seconds. That the simple random sample, there is a 15% chance the mean time will be at or below 57.38 seconds. And that's how we would do that. That's it.